So now that we've seen this, as you saw yesterday, a lot of the work that we do at Cerebrus is because of the unique architecture we have. And one of the benefits of our architecture is that you can do sparse compute. So, there's something we've all seen that, over the last few years, the size of these models have been getting larger and larger, right? It's growing exponentially. And more often than not, we're seeing that, compute becomes a bottleneck where, it's not scalable or feasible to run these even on thousands of GPUs and things like that. And so while, the Cerebrus hardware provides benefits in terms of that, so you can go even bigger, eventually even that would get hit. You would eventually reach a limit even there. And so one of the things at Cerebrus we've been thinking about, and thinking about the community, is we need a way to gain more out of these models. And we do know for a fact that, these models are highly overparameterized, right? We've seen, especially in the more recent cases where we've seen 7 billion models competing with GPT-3 and things like that in certain aspects, we do know that smaller models might be able to compete as well. But, one other dimension of trying to introduce a smaller model is sparsity, right? Now, in traditional hardware, people tend to think about dense flops, whereas Cerebrus is the only system where you can accelerate AI with any sparsity. And there's been some past work where we've shown, not just us but others in the community have shown, that if you can introduce sparsity, the number of flops you're training reduces drastically, but you can still attain the same level of accuracy and downstream tasks, right? Now the challenge has always been the hardware was never available for you to get that speed up, and even deploying a sparse model on existing hardware was always challenging, right? With Cerebrus, that's no longer the case. So I'm going to walk you through a sparsity demo where I'm going to introduce essentially random sparsity into the weights. So we'll be doing weight sparsity here, where we're initializing the weights with us. In this case, we're going to be doing a 90% sparse model. And you would see the flow looks pretty much the same. I'll again show you the difference between the YAML files on what changes I made. And then I'll walk a bit further deeper into the sparsity itself. Any questions before we get into that? So just like the previous ones, right? We have, the same run.py, no changes. Again, very similar commands. We're saying I want to run on the CSX. We want to do weight streaming. I'll show the difference between the YAML and the original, and everything else is identical. And then I think there's a question. Okay, I see someone else has answered. Perfect. And then if you look at the only difference is essentially I've added a few lines where I'm saying I want to do sparsity of 0.9. I want it to be random sparse, and I'm setting a seed so I can reproduce the results. That's pretty much all that's needed to introduce sparsity into this same 1.3 billion model, except now it's going to be, well, certain attention layers and things are going to, certain layers are going to be 90% sparse. You could sparse any layers that you want. As you can see here, we do have a way for you to specify which layers exactly. In our case, we tend to stay with the more dense, large layers, mainly because that's where we get the most return for the sparsification. And as you can see here, again, we're compiling the model. We're only sparsifying 144 of the 1,900 weights that are totally available. And again, this is going through the compile process. Let me see if I can show you that before compile completes. Typo there. Hasn't started yet. So the compile, there is two parts to it. One part which happens on the user node, and the other part which happens on the wafer or on the cluster. So as you can see here, this is running a compile job. The way you know it's a compile job is no system has been allocated to it. So it's only using compute resources on the cluster, but not actually using the actual system to do the compile. So you can do compile even if the systems are occupied otherwise. Compile has been successful, and now it's going to try spinning up the execution job. So I know yesterday there was a question where people want to know if it's a single command to do both the compile and train. As you can see here, we only launch one command and it ends up doing the compile and training accordingly. And now if we can see that we're using one CS-2 here. And as you can see here, and we've started the training soon. As similar to the previous runs, you will see that the weights will start getting transferred, and then we'll start seeing the losses, and then we can see the results on the tensor board, and we can see the performance gain we get with it as well.
As a quick question on sparsity. So what are the ways that we can try out running models with sparsity? Is it through the config files, or do we have to tweak something in the model as such?
If you're just trying to introduce weight sparsity as such, you don't need to modify the model itself. You can think of it as essentially two different ways you could do it. One is, so we provide some ways of doing. One is, as I go here, I can show you, we have random and top K. So random, as you can imagine, is sparsed randomly, and top K is it takes the weights of the lowest magnitude and essentially turns them to 0. Another way, if you really want to do this, would be to, you could essentially specify through checkpoints itself, essentially. And we are going to be adding more methods so you can do this, or you can, in theory, you can write your own versions of this as well in the code. But out of the box, we provide these two approaches where you can introduce sparsity, and the only change you need to do is the YAML change I showed earlier, and that's about it. You don't need to, this is the only change you need to do to introduce sparsity for any of your models.
A quick question, if you change the sparsity level, do you have to recompile or not?
If you change the sparsity levels, it does. So yes and no. So you will need to do it because at this point it's fixed sparsity here. So it enforces that, throughout the time you're seeing the same level of sparsity on these weights. So therefore that does affect the compile. There is a new compile that takes place because of that. If you're just doing like initial sparsity at the very beginning, but you're okay with the weights, non-sparse later on, let's say you're doing at the checkpoint level, then you wouldn't need to do a recompile. It'll reuse the compile from earlier. So, like last time, it'll spin up a tensor board for us. We can start seeing the results soon. So as you can see here, this is again just using one system, but when we switch over, we'll be able to see the performance difference pretty quickly. And again, this is essentially running the same 1.3 billion model with some induced sparsity now. While we wait for this, I can kind of walk a bit more in detail on why sparsity works so well for us, right? So, one of the biggest challenges when you're using any hardware is you're trying to find the balance between, compute bandwidth versus memory bandwidth and how much data flow you can have. On GPUs or traditional hardware, the biggest challenges tend to be because your bandwidth is quite low, you can't transfer, for every byte you transfer over, you want to use it for as many flops as you can. And so, matrix computation tends to work well there, right? That's why we tend to stay in that realm. Because of the change in architecture, as well as the high bandwidth that's available on our wafer scale engine, we can actually transition away from that, right? And so we can essentially go all the way down to a vector scalar multiplication, right? And this works great because your sparse general, sparse matrix multiplication is essentially just a many AXPY, many vector scale multiplications happening together, right? And so we're able to tap into this sparsity benefits that is not traditionally seen on any other hardware. And so this is one of the benefits of of the Cerebrus cluster, is that we are able to do this. And as I was showing you guys, right, there's no any real change that's needed to the weight streaming model, right? The sparsification happens on the memory X, where we convert the weights, introduce the sparseness, and then transfer it over the SWARM X to the various systems and receive it back. So the weights are sparse, the gradients become sparse, and then we do the updates in sparse form. And so this essentially, between the data flow and our high bandwidth, we essentially get sparsity. We can support sparse models just the same way as dense. So there's no difference in terms of execution model or what's happening, whether you're running a sparse or dense model, in terms of the code change you need to make or anything beyond just choosing what kind of sparsity that you would like to have. Right, but in terms of at a high level, it's the exact same behavior and usage for a user to get the benefits of this. Let's see if we're starting to see some losses and some performance here.
Vishal, we also got a question. Someone cloned from our model zoo on GitHub, but can't find the default and sparse YAMLs you're using in your demo. Can you point to maybe those locations?
So the default one is I can quickly show that. Maybe once this run is done, I'll just show you what the default is. The default is essentially the same as the original one I showed you, the params gpt-xl.yaml that we used. I think the only difference is I may have tweaked the batch size a little bit, so just so that we can see some behaviors more cleanly for this demo purposes, because I think that was set up for more performance uses. So, but other than that, I can show that quite quickly. I can show the difference between those, and it should only be a minor change. And then all the other ones, as I've been showing, has only been a small change from the default itself.
A quick question on the sparse weights, right? So when you're kind of streaming those sparse weights, say if it say a 90% sparsity, right? So do you still do that on a layer by layer basis?
Yes. So when we're streaming onto the wafer, yes, we still send it based on the computation. Because we know these weights are going to be sparse and we're going to maintain it, it does reorganize what type of compute how we reorganize the compute on how it's going to be shifted back and forth from the wafer, right? So we may group a few more operations, or depending on the size of the model and things, right? But as at a high level, yes, the weights are still streamed on and off the wafer.
Okay, yeah, I think it makes sense to kind of may fuse with other operators or that can help with the utilization, right?
Exactly, yeah. So as we can see here, again, we run it for the same number of steps. And you can see though the loss starts higher. So demo 3 here is our sparsity run. Though we started a little higher, it starts converging back to almost the same as the first 2 runs. Again, I have not even made any changes. And obviously these are still very early stages of the loss. More interestingly, if you look at the actual average steps that it takes for us between the runs, we see that the 90% sparsity is giving us essentially a 2x speed up as well, similar to the linear scaling of running on 2 systems, right? So I think there was a question on how much speed up can we expect, right? So with, like, for example, in this model with the 90% sparsity, even though we're only doing it on a subset of the weights, we see almost the same performance as if we were just running dense on 2 systems. So that's the kind of benefits that you see on sparsity on our hardware, which is harder to see on any other hardware out there. Hope that answered the question, Vision. I think that was your question. And then quickly before we continue, let me just show the configs where I got it from. So this is the default, the original one, and this is by default. As you can see, the difference is I've essentially just changed the data directory to point to on the ALCF from our default path. I've changed the max steps and how often we log, just so that you can see the results more quickly and we're not here for a longer time than needed, and that's about it. That's the only change. So just pointing to the right directory and then running for a fewer steps is the only difference. I didn't want to touch the default model zoo here in case somebody wanted to go through that as well. But so that's where the default comes from, and then obviously the other ones, both the two systems and the sparse, I've shown the diffs. As you can see on the right hand side, you can see the diff between the default and the sparse, and then you can show here as well the difference between the default and the two systems, which is just accounting for the two systems and the corresponding batch size. So we're still running with the same global batch size. So we're comparing the same two models. Does that help? I'm sorry, so I don't know who tried cloning it, but I'm hoping this helps clarify the YAML files. Okay, any questions? If I remember correctly, I think we have. So, okay, so there are a couple of questions. Which sparsity strategy works best? I would recommend referring to the paper that I had in the slide deck here, where we kind of go through the different ones. So this is some of the work that we have seen where we do sparse pre-training and then followed by dense fine-tuning. So we're essentially using much lesser number of flops, but still essentially gaining the same level of accuracy on downstream tasks. Bill Arnold asks, how does densification work after sparse training? So when we return back the checkpoints, we still store them back in a dense format. So you can take those checkpoints and then reuse it to do inference or a dense training and so forth. Hope that answers your question, Bill. Constantino. Yeah, thanks, Murli. Murli, I think, shared the link to the paper, which kind of walks through the more details on, how you identify what's the right level of sparsity to use and what works for your models, and what has some of our researchers found, in as well as some of these papers that others have shown in the industry. Yeah, thank you, Murli, for that.